Hey guys, this last section is over logistic growth functions. Kind of a shorter section today. It is an extension from the problems that we have been doing. So this is what a logistic growth function looks like. We have some constant divided by 1 plus a times e to the negative rx. It always looks like that. So we will plug in values for a, c, and r to solve or to graph this function. So where it says evaluate f of 6, that means where you see x, we're going to put a 6. So just type it into your calculator, and you want to make sure as you're typing this into your calculator that you have 10 divided by, and then this gets grouped together, and then instead of x, you'll put the 6 in there. So work with those grouping symbols. You should get approximately 9.83 when you plug all of that in. So pause the video, try that now if you have not. If you would, just go ahead and type that into your y equals without the 6 in there. So you're going to go back to using the x in there. I want you to just take a look at what this looks like. We're not going to spend any time on the table right now because we're going to talk about on the next slide what it's going to look like. But I want you to see what all of these functions look like. They start off low, and then they go up, and then they level off again. And there are different real world applications where we see this. One of these is a population. Think about deer in a forest or insects that you may see a rapid incline, and all of a sudden there are a lot of animals somewhere, but at some point there are not enough resources to hold that many in a population, so it levels off at the amount that it can handle. So you may see these logistic growth functions in something like a biology or another science class. So properties that we know: y equals 0 and y equals c are horizontal asymptotes. So notice c was that numerator value. We're always going to be at y equals 0, and then that numerator value are going to be the top and bottom values where everything will occur between. Your y-intercept is 0 and then c plus 1 over a. So no e to the negative rx. We just take that off to find our y-intercept value. So point of maximum growth is the natural log of a over r, and then c divided by 2. Domain, all real numbers, so negative infinity to positive infinity. And then our range, as we talked about, is going to be between those horizontal asymptotes, so anywhere from 0 to c. All right, so let's try to graph one of these functions, and let's just use those properties that we know. So we have y equals 3 over 1 plus 5e to the negative 2x. So I know that my asymptotes are going to be at y equals 0 and y equals 3. So I'm going to go ahead and plot this. And I'm going to go by halves so I can fit these in here. So y equals 0. So it's not so tight in where we're graphing. So y equals 3. So then my y-intercept says that it's 0, and then c over 1 plus a. So 3 over 1 plus 5. Well, 3 over 1 plus 5 is 3 over 6. So it's 0, 1/2. So I'm at 0, 1/2. The point of maximum growth And so that point of maximum growth is like that midpoint. It's that turning point on the graph where we go from increasing to starting to level off. So it's the natural log of A, so point of max growth. So we have the natural log of 5 over R, and our R value is 2. It's not negative 2 because it's just the R value, and since that does have a negative in its regular equation, it's e to the negative rx, then we are at positive 2. And make sure you keep that in mind. And then it's c divided by 2, so 3 over 2. So the natural log of 5 divided by 2 is about 0.8. So I'm going to be over 0.8 on the graph. And then I'm going to be up 1.5. So I'm going to go again by halves here just to see a little more spread out on the graph. So 0.8 would be about here, and up 1.5 would be here. So that's where the graph starts to level this direction, and then it goes like this. So that's how you draw that. If you know those key points, the graph is not difficult to draw. That logistic growth function looks complex, but when you know those key values, that's all you have to do to be able to draw that graph in. So sometimes it will ask you to solve these. And you can choose a couple different ways to solve. You can think of it as 2 proportions, so put 10 over 1 and cross multiply. I tend to just multiply this denominator over, so I get 30 equals 10. So we want to know when y is equal to 10, when we are set equal to 10. So 1 plus 5e to the negative 2x. From there, it looks very tempting to multiply and distribute that 10 out, but I really would just divide by 10 on both sides. So then 30 divided by 10, we're just dealing with 3 equals 1 plus 5e to the negative 2x. You can multiply the 10 out, you're just going to deal with bigger numbers then. So here I'm subtracting 1. So I have 2 equals 5e to the negative 2x. Remember, our goal is to try to get that e to the negative 2x by itself. So I'm going to divide by 5 on both sides. 2/5 is the same as 0.4. Since I know I'm going to have to plug it in the calculator eventually, I'm going to go ahead and change that to a decimal. E to the negative 2x. From here, I'm going to go ahead and switch this over so I get the natural log of 0.4 is equal to negative 2x. And then I need to divide by negative 2. So important when you type that into the graphing calculator, you close off the parentheses after that 0.4, or you hit enter before you divide by negative 2. When you do that, you should get x is approximately 0.458. Alright, and that's it for our extension today. So we are all finished with our logarithms chapter. So if you have any questions, please come in and see me. Otherwise, I will see you in class.